Good afternoon, everyone. My name is Alexandre Valentin Jamet, and I'm currently a second-year PhD student in the Barcelona Supercomputing Center. During this presentation, I will be presenting our work on the characterization of the impact of cache replacement policies on big data workloads. But first, an introduction to our work. For decades, the performance of both CPUs and memory systems have been consistently increasing. While CPUs were following Moore's law, the performance doubling every 2 years, memory systems followed a mild trend, thus leaving an increasing performance gap between them. In an effort to hide the high main memory latencies, computer architects introduced caches, small and fast on-chip memories retaining valuable data close to the CPU. Due to their small size, caches come with replacement policies, an algorithm designed to decide which memory block must be evicted, hence answering the question, how long in the future will that block be useful? As we said in the previous slide, replacement policies are answering the question, how far in the future would that block be useful? Replacement policy is a thoroughly studied and explored topic. When it comes to the well-known SPEC CPU 2006 and 2017 workload. However, when it comes to new workloads, gap, XSBench, and so on, that exhibit poor temporal and spatial locality, we showed that state-of-the-art replacement policies are helpless. The methodology used to obtain this figure is the same as reported in slide 26. As we can see, gap and XSBench with LLC MPKI of 78 and 37 are much more intensive than SPEC. One can also see that when we are talking about speedup over LRU, state-of-the-art last-level cache replacement policy incrementally improve over time for SPEC workloads. However, we observe that these policies struggle at generalizing to other workloads. Now we will review the benchmark suits used throughout this work. To start with, in our working set of benchmarks, we decided to include SPEC workloads to provide continuity with previous work. SPEC CPU 2006 and 2017 are composed of typical, commonly used workloads encountered in a variety of situations in computer sciences. Compilers, data compression, AI algorithms, and physics simulations account for most workloads. We also included a set of workloads provided by Qualcomm in the context of the CVP1 contest. This set of workloads is a mix made of server database workloads such as MongoDB or Redis. The gap benchmark suite is another set of benchmarks that we decided to include in our work. They are representative of graph processing, an emerging class of workloads. They find application in many sectors of the computer sciences industry and in everyday life products. Going from social networks to discover communities and suggest new relations, finding the shortest path to your home is also a canonical example of graph theory, which is nowadays solved in your phone by your favorite GPS application. Search engines are also good practical examples of the usage of graph theory, knowing that the proposals are partially based on the connectivity of pages. Nonetheless, graph processing workloads exhibit properties and behaviors harmful for CPUs and the cache hierarchies. Among these properties, one can find very large memory footprint and highly irregular access patterns, both leading to a massive impact on caches as shown above. The gap benchmark suite is shaped with both graph kernels and inputs. When it comes to kernels, authors argue that between centrality, page rank, triangle count, and the others available are representative of workloads running in both industry and academia. Conversely, a set of graphs is also provided. Trivial graphs, a web crawl, a graph of the roads in US, and a topology of tweets on the social network. Also, two synthetic graphs are also provided. One is based on the Kronecker algorithm, and the second one is the uniform random distribution graph. In this work, we use each of the 30 kernel and graph combinations available. When it comes to the technical details, the CSR format is used to represent graphs in memory in an efficient manner. However, this organization in memory leads to indirect memory access patterns, which are tightly related to the graph topology. Eventually, the property array, which contains the actual working data, is traversed with no specific pattern. To show how irregular the access to the property arrays looks like due to the CSR format used, To represent the graphs, let's have a look at an example with PageRank and a tiny example graph. Two consecutive elements of the offset array make a slice used to index the column array. The values obtained from the column array are used to index the property array. Knowing how to traverse the graph, we can then proceed on that example. As you could see in the previous slide, there is no particular patterns in the way the property array is traversed. And this behavior will just be increasing with the size of the graph. Last but not least, XSBench workloads. These scientific workloads intend to approximate the behavior of OpenMC, a nuclear physics simulation tool, by exposing only its core components. Such benchmarks have the particularity of randomly selecting inputs for the main loop of the workloads, which eventually lead to hard to predict access patterns and poor cache utilization. Now that we have presented the workloads, we will continue by presenting a couple of state-of-the-art last-level cache replacement policies. First, reuse distance prediction. Both proposed by Jalil, SRRIP and DRRIP, are two mechanisms aiming at classifying blocks into re-reference intervals. Going from immediate reuse, meaning that that block is perceived as experiencing good locality. Conversely, a block can be classified as distant reused, meaning that it is supposed to be reused much further in the future. This classification is achieved through RIPV, re-reference prediction values, which are assigned to each cache block. On an insertion, a block with maximum RIPV is searched, in this case, a value of 3. If none is found, blocks are iteratively aged until a matching block is found. Then the selected block is replaced by the missed block and an RRPV of 2 is assigned to it. On a hit, the block sees its RRPV change to 0 to reflect the recent usage. When it comes to signature hit prediction, even though the name says the opposite, the mechanism is actually a dead block predictor. Based on a simple SRRIP policy, this policy identifies signatures that tend to produce dead blocks and push them towards eviction. For instance, a block inserted through a PC that previously showed a dead block behavior would be inserted in the distant reuse position. The Multiperspective Reuse Prediction is also a dead block prediction mechanism backed with a bypass policy and a couple of optimizations over its base 3-base PLRU policy. This prediction mechanism is made of two main building blocks. One, a sampler in charge of generating learning signals for the predictor. Two, a hash perceptron predictor that learns correlations of features with the provided learning signals. Features, another key component of this replacement policy, can be thought of as elaborated hash functions, designed to extract valuable bits out of PCs and physical addresses. The features used in the original work were obtained thanks to a gradient descent algorithm, introducing small perturbations in the set of features in order to minimize the LLC MPKI. On an access, the hash perceptron is indexed and builds a prediction based on the access characteristics such as PC, physical address, and so on. On a hit, if that prediction exceeds a threshold, the block is not promoted to the MRU position. On a miss, the prediction is compared to a handful of thresholds, and depending on which threshold it exceeds, the block can be either bypassed or inserted in positions closer to eviction. Jane, through her work on replacement policies from the Hawkeye predictor and her latest creation glider, used a component designed to dynamically approximate Beladay's main replacement policy based on a partial history of accesses. As it is a rather complex piece of science, we won't go into details but encourage you to have a look at these publications. This component, named OptiGen, generates binary learning signals and trains a predictor. This predictor is then used to produce predictions and to trigger actions such as inserting in the distant reuse position. Now that we have presented the state-of-the-art replacement policies, we will present two derived designs of the multi-perspective that we propose in this work. As we saw at the inception of this presentation, when it comes to the freshly introduced workloads, the replacement policies shown above are having a hard time generalizing. To cope with that, and in an effort to adapt to the different natures of these benchmarks, we provide two new replacement policies design. These policies try to adapt the features used to the different phases of a workload. First, we present MS-MPPPB, a modified multi-perspective making use of multiple samplers and hash perceptrons. On an access, all samplers are accessed in parallel and train the associated hash perceptron predictors. When a prediction is required, a scheduling mechanism compares the performance of each predictor and requests a prediction to the best behaving one. Our second proposal is named DS-MPPPB for dynamic selection and tries to dynamically adapt the features used for prediction. In this design, we train a wide set of 64 features and track their quality thanks to what we call a coefficient. In this design, all features are always trained. When a prediction is required, the 16 features maximizing the sum of their coefficients are used and indexed. The weights obtained from the prediction tables are then summed the same way as the original multi-perspective. Before showing our experimental results, let's stop for a second on the methodology. We used GemSim, a detailed trace-based simulator that models an out-of-order CPU and its memory hierarchy. In order to obtain the input traces of the simulator, we used the SimPoints methodology to obtain up to 10 traces per workload, of 1 billion instructions each, using only the ones representative of at least 5% of the workloads. Now let's move to the results and discussion on them. As we saw at the very beginning of this presentation, when applied to the newly introduced benchmark, recent state-of-the-art replacement policies fail at generalizing. In the following slides, we show both MPKI and speedup results for some of these replacement policies applied to the most intensive workloads. Further, we provide evidences on the observations made here and focus on graph processing workloads. When it comes to LLC and PKI results, we only show the 50 most intensive workloads using the LRU policy. All workloads shown on the figure exhibit a much higher LLC and PKI compared to the previous works with an average of 120. On the speedup results and dealing only with state-of-the-art replacement policies, it turns out Multiperspective is more versatile than Glider and is able to deliver good performance even facing very complex workloads. As a matter of fact, Glider gives a geometric mean speedup of 5% while Multiperspective goes up to 7%. This shows the need to include more workloads in the training of these replacement policies to allow them to generalize to different behaviors. When extending results to the two proposed designs, we see that their ability to change the features used to build predictions depending on the phase of workloads they are facing allow them to deliver higher performance improvement with a geometric mean speedup over LRU of 8% for DS-MPPPB and 8.3% speedup for MS-MPPPB. To better understand the results shown above, we analyzed the behavior of the benchmark suits through a measurement of the reuse distances of the last level cache blocks. Reuse distance is defined as the number of accesses to distinct blocks, separating two usages of one block. For example, with an access pattern of ABA, the reuse distance of A would be 2. Also, if the reuse distance of one block is at least 16, this block is considered as dead, otherwise it's alive. Based on the figure and the table showing reuse distance distribution for each benchmark suit, it is quite clear that SPEC and Qualcomm workloads are biased towards a cache-friendly behavior. With a median as low as 10 for SPEC and 4 for Qualcomm, most cache block gets reused before eviction. Some Qualcomm-intensive workloads might see very long reuse distances as the maximum seen is around 60,000 accesses. The average proportion of accesses to dead blocks confirmed the overall observations. When it comes to XSBench and gap workloads, the story is completely different, as they show very distinct behaviors from the one of the SPEC and Qualcomm workloads. XSBench, with an average reuse distance of 343 and a standard deviation of 876, show a much more cache-averse and hard-to-predict behavior. The median reuse distance of 61 gives a strong intuition that most blocks shouldn't be inserted in a cache. It is then straightforward that XSBench are cache-averse workloads. Last but not least, gap workloads. As we described above, due to their nature, they demonstrate an extremely cache-averse behavior. The average reuse distance is up to 908, while the standard deviation tops at 2106. And the average proportion of blocks never reused goes up to 55.84%. All these parameters are highlighting the fact that not only replacement policies are struggling with these workloads, but the caches and their underlying assumptions. Overall, we observe that cache replacement policies are impractical solutions to tackle these very complex workloads. Here, we focus on the gap workloads to explain the correlation between reuse distance figure and input graphs. As you can see, Kronecker and Uren graphs lead to longer reuse distances. The two bottom figures show degree distributions in Uren and Webb. It turns out Kron and Uren are two graphs with either a high average degree or a highly skewed distribution. These two characteristics tend to make access patterns even more irregular and lower cache utilization. Other than the average degree and the shape of a distribution, the number of edges and vertices in a graph are good explanatory variables. Now that we have presented results and explained the origins of the very complex behaviors of graph processing workloads, let's move to the conclusions of this work. Throughout this presentation, we saw that previous work on cache replacement policies provided important performance benefits. However, this work focused only on a reduced amount of CPU-centric workloads. When applied to new HPC and big data workloads, these replacement policies fail at generalizing well. We then proposed two new designs able to adapt themselves to these new workloads, MS-MPPPB and DS-MPPPB, respectively leveraging 8.3% speedup and 8.0% geometric speedup over LRE. Eventually, we provide intuition on the behavior of these HPC and big data workloads with a strong focus on graph processing.